You too. All right, welcome. I see you survived the weekend. Anybody have any Newton's first law inertia slipping demos? I hope not. I didn't drive my car all weekend because I know I would have. They don't seem to plow my street, the two main streets, but not mine, so I didn't go anywhere because I wouldn't have made it back home uphill. So I got rides everywhere. Did you guys observe any cool physics over the weekend? Your tire broke? Oh man. Yeah, I have just front wheel drive and my tires are lousy. So I pushed about 4 different vehicles and shoveled a couple people out. Anyway, welcome back to a new week. I have read through all of Homework Zero's responses, the Get to Know You web assignment, and I'm impressed. Any physics class that I've taught before, one, and that you guys took it seriously. Thank you. That was always my hope so that I could learn stuff. Too often people are like, do you like science? Yeah. So I have to throw in the why because I just get kind of these lame answers or these trite answers that I can tell you're just answering it. But you guys took it seriously. Thank you for that. And two, I was more impressed because you guys really do like science. You guys have a passion for it, I can tell. I know, not everyone, but more than I think any other class I've taught. So that means we can have fun. I love teaching this level and this type, this environment, because I get more excited about it. I love seeing when light bulbs go off. I was an engineering major for most of my undergraduate career, and obviously I have respect for them, but they're, sorry if you're going into engineering, but it's true, they're a little more boring. They get less excited about cool science things because, I don't know, they've been studying it all their life or that's what they expect. And so sometimes it was anticlimactic. So that's why I like this class. Have fun. Anything else you want to bring up before I delve in? Okay, well I need a volunteer because I didn't get to do one demo I wanted on inertia. So, want to help me? Come on down. Come around here, if you will. Do you trust me yet? You think so? Okay. I would like you to put this on your hand, and if you come on this side, then they can see you. Okay. You can rest it however it's comfortable, because then we're going to whack. And if you want, I'll do it first. But you look like you're trusting me. This is a lead brick. The brick itself weighs 26 pounds, so this part's uncomfortable in and of itself. Yes? Yes. Well, here, tap yourself, the brick. Does that hurt? You think you can do it harder? Yeah. How hard do you want to go? Give it a good one. All right. Here, we'll spare you. You got any ideas why this might not kill you or crush your hand? Lead. Because it's lead? Maybe. Or yes, we'll go with that. That's partial credit. Right. From educated guess now, hypothesis. Based on what we've already covered thus far, what can you say about that brick?
It's very dense.
It's very dense, correct. Help him out. It's got a lot of mass. Good. Which implies it also has a lot of inertia. And inertia is resistance to change. So you're trying to push it down. Here's a force, right? And you try to accelerate it down into your hand. Change of motion. It wants to resist that. Just like you can whack it sideways. It didn't move very far. Where if, I whacked that. So it wanted to move, but it was resisting that because it has more inertia. So it doesn't smash into your hand like you think it would. Thanks. That's why Superman can't see through it. Yep, doesn't work. No, I'm not implying I'm Superman. But it is fun. That is the most uncomfortable part. But yeah, you can. It's just if you miss, then it hurts. But seriously, that doesn't hurt any more when you whack it than when you're not whacking it. I did it once, a tree stump. It might be easier to get your hands on. You could nail a nail into the wood of the stump while it's on your head. If it's big enough and has enough mass, it won't hurt. You'll feel it, yes, I won't lie. And the more massive it is, the better. Have you guys seen ever somebody lying down on a bed of nails? And they put the cinder block on top and they crush it? Yes, I have that demo. I've done it. But there's one main reason why it doesn't hurt. It's actually worse having somebody stand on top of the bed of nails while it's on top of you, because they have more weight. The cinder block's not as heavy, but it does have a lot of mass. And when you hit it, it resists that change. And so it's very similar to this, and it breaks apart. And it's spreading the force over a large area, which we're going to study later, Pascal's principle. Some facts they've learned, hypotheses they made that have been really well tested and verified. And it never seems to contradict it. So they made it a principle that force over an area exerts less pressure. Anyway, I wanted to show you that one. Today, we're going to start Chapter 3 on linear motion. And we'll get through Chapter 4 by the end of the week. So 3 today, might finish it up Wednesday, start Chapter 4 on Newton's second law, and then we'll finish up Newton's second law Friday. So Chapters 3 and 4 this week, and that's what your homework will be on this week. 3 is on linear motion, and as much as we all dread memorizing a few things, there's some terminology we need to have in common so that we can go forward the rest of the semester. If you haven't looked at it yet, you've probably heard of every one of these terms and pretty much already know the definitions. But we're going to make sure we're all on the same foundation and that you understand them the way a scientist understands them, lest you have any misconceptions. Chapter 4, then, we can use that with Newton's second law and how these forces cause objects to accelerate. That's pretty much what Newton's second law is about. Questions, concerns? Okay, I know. Thank you. A couple of you have emailed me about clickers. Long story short, I'm fair. Don't worry. I'm going to work this out. I won't penalize you. The guys on campus with the software and me using it and connecting up and integrating is not working smoothly yet for me. Thus, until it does, I won't hold you accountable. You'll all get credit or I won't count it. Don't worry. But he's emailing me. I saw he responded to all my questions as soon as we were starting class, so I haven't read it yet. But those that did email me, I could see your device ID number. There were a few that emailed me. I could see it. But if you have not registered this with your ID number, you won't ever get credit. And if you're using a mobile device with responseware, like your phone or laptop, you must buy the license so that you get an ID number that they send you in your email, or it won't work. One student made me aware that they were able to create an account in responseware and log in, and it seemed like they were responding, but that's not going to work. You have to buy a license and get an ID number so that it'll integrate, and I know who you are. It won't always be random. Does that make sense? Great. It's all in my syllabus with the links. I got links to responseware. There's actually a whole user guide that will explain it more than you want to know. But the links are there to go, and you'll see create an account, buy it, purchase a license. Well, you're doing the clicker, so you just go to the register your clicker. I got a link. You enter the ID number on the back, and it'll associate your clicker with you. So every time you respond, I can give you credit. Good, I almost forgot that. Alrighty. Motion is relative. That's how this chapter starts. And that means when we say something has motion, we have to give it a reference point. When you're saying you're going 80 miles an hour down the highway, that's with respect to what? You're in a car, so respect to the motion of the earth? That's one way we could do it, but usually when we say 80 miles an hour, it's relative to the ground, which for all practical purposes is not moving. But he brings up a good point. Technically, the earth is moving relative to the space around it and the sun. But we don't want to deal with calculating that every time. But that proves my point. Motion's relative. And so when you say a speed or an acceleration, you're going to have to take in mind what that's relative to. And that will help you solve some of these conceptual problems. When it's not stated, you can assume the obvious. Like, oh look, I threw this at 10 meters per second. That's relative to the room that's not moving around us. If that matters and we're starting to get funky, we'll tell you. Einstein, if you've studied him at all with his theories of relativity, did not take this for granted. And he came up with stuff called reference frames. You don't need to know this. I mean, I'm not going to test you on it. Reference frames. And so we would say, like, this room is a reference frame. And so relative to it, we can do experiments. But if we assume the reference frame is our solar system, then we do have to take into account the motion of our room moving on the Earth. One, the Earth is spinning, so there's a speed, a motion. But the Earth's revolving also around the sun. That's a different motion. Our solar system is revolving around the center of the galaxy. That's another motion. And our galaxy is moving. You get the point. So what is speed? Chalk. We need chalk. Speed. Who wants to define it? Take a stab. You probably already know. Somebody does, I'm sure. Distance over time? Ding, 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 ding. You're correct. So here's an equation. You can use it to solve. Right now, it's a relationship. Speed is you travel a certain distance, and it takes a certain amount of time. So when you're going 80 miles, if that takes 1 hour, then your speed is 80 miles an hour. Most people get that? So it's like, you can think of, usually when we say how fast, something's moving. We're talking about speed. Now, there's two types of speed. Instantaneous and average. These are in your book, so when you forget what I said. What's instantaneous? In an instant, yes. It's at a specific moment in time. So if you're in your car, keep on this motif, 80 miles an hour right now. But if you speed up and slow down, at any given moment you could be going a slightly different speed. At those instances, that would be your instantaneous. What does your, oh, no, wait. So what's average? Over a course of time, yeah. Think of it as over a certain distance or over the certain time. That's like a trip. How long it took you to get here from home? You went yay far. Still distance over time. Both of these are still distance over time, but look at which one. Instantaneous, this is really small. It's like you got to pick a little small interval and say, right at that spot or right at that moment, how long did it take? And that'll tell you how fast you're going. But if you say over the whole trip, you'll get an average. Because you know you start out slower, and then you get on the highway and you're going faster, and then you slow back down, and then you have to brake because the car in front of you doesn't know what they're doing. And then you turn, and you're always changing your instantaneous speed. But on average, then we'd say, we were going 30 miles an hour. So this car accelerates. Whoop. It's going slowly. And then quickly, slowly, quickly. So right here, its instantaneous speed is slower than right here. But the average would be, we could take this distance and divide it by how long that took. If you want the instantaneous right here, well, you got to pick some interval. Let's say, an inch from here to here. Yes, sound effects help. And you time how long it takes to go from there to there. It's still a distance divided by time, but right at this moment. And obviously, the smaller you make that interval, the more accurate you are for that instant. But you get the idea? So what's your speedometer in your car tell you? Which type of speed? Instantaneous is correct at any given moment. Physicists like the term velocity. You've heard it before. How does it compare to speed? Is it different or the same? Hey, somebody's read it. It has direction. So we now will speed with direction. Scientists like to use two other terms, so I'll expose you to them. A scalar and a vector. Scalar is when it's a magnitude, a number, an amount. Speed is a scalar. "80 miles an hour. That's a scale. It tells you how fast you're going, but not in which direction. North, south, up, down. That's a vector. A vector adds direction. So that's like velocity. And that's very important in physics, that distinction. You'll see why more, trust me. So 80 miles an hour is speed. 80 miles an hour north is velocity. That make sense? So when you're just talking willy-nilly to your friends, you might use speed or velocity interchangeably, and it might not matter. But if that direction is important, then you'll need to specify. I'll give you an example before this lecture's over. Are we good so far? You guys will let me know if you got questions, right? I don't. Again, this is your class. The point is for you to learn. Let me help you. So, okay, good. Don't worry, it'll get more complicated. And I'll help you through it. We'll do it together. So, how would you define acceleration? Speed over time? I can go with that. A rate of change. I go with that. You want to add anything? That's how I define it too. Rate of change. Let's emphasize what is changing. Be more confident. I heard it, but it wasn't very loud. Had 3 syllables. I know I heard it. Okay, what's changing? Speed. It's not what I heard, but yeah. To make this one more accurate, and I actually hope you did write speed down in your notes already, because this will remind you. Technically, it's velocity over time. So the rate of change, that's the key here. Something must be changing. A change of motion, change of velocity. That's the key to acceleration. We're comfortable with how fast. That's speed. But the change of how fast, or how fast it's changing, that's acceleration. And the reason it's a velocity is because you are accelerating when you go from 0 miles an hour up to 80 miles an hour. That seems like a change in speed. Well, remember, velocity includes speed, but it also has a direction. So when you turn a corner at 80 miles an hour, you don't change going 80 miles an hour. In other words, your speed is not changing. But if your direction changes, do you think you're accelerating? In physics, yes. A lot of people don't realize that. So again, 80 miles an hour, speed isn't changing. If I turn at 80 miles an hour, I am accelerating. It requires a force to do that, and that'll make me accelerate. We'll cover that next chapter more. So velocity, having that direction, being a vector, is important. Because you can accelerate by speeding up, slowing down, or changing directions. There's 3 ways to accelerate. Let me pause and go back up here. Units. In science, we like to use standard units. So the world has standard units, and us in America, with our funky system still, can play along. Distance standard unit is meters. We'll just meter. And time is second. So speed is measured in meters per second. So velocity is also, velocity is meters per second with a direction. Meters per second, north, south. We've already seen this one, but acceleration,
When do you have the squares?
right now. Good question, Brian. When do you add the squared? A change of velocity. I like to sum this one up as acceleration is the change in velocity over time. This symbol, this triangle, is called delta in Greek alphabet. It represents change. So this means acceleration is the change in velocity. Change in velocity over time. Shorthand notation to represent what we've just been discussing. Velocity is in meters per second. Acceleration has that over time. So acceleration is measured in meters per second per second. Meters per second per second. We get tired of saying that. Meters per second per second. As much fun as it is, meters per second per second. We just call that meters per second squared. Technically they're the same thing, but we like to write meters per second squared. And the reason I emphasize meters per second is conceptually it'll help you solve a lot of problems. Acceleration is a change in velocity. It's the rate at how fast you're changing, how fast you're going. So if somebody is accelerating at 10 meters per second squared, and he starts at rest, so you're not moving, and you're going to accelerate at 10 meters per second squared, 10 meters per second per second. After 1 second, how fast will I be going? I'm going 0, I'm at rest. I'm going to accelerate at 10 meters per second squared. So after 1 second, how fast will I be going? 10 what? Just to get you in the good habit. It's correct, 10 meters per second. Yeah, because my change, I'll pause. My change in velocity was from 0 meters per second to 10 meters per second. That's how much I change in 1 second. So after 1 second, yes, I'm going 10 meters per second. You follow? So how fast am I going at the end of the second second? 20 meters per second, because I just changed another 10 meters per second, from 0 to 10 meters per second in the first second. Another 10 meters per second change in the second second. So now I'm going 20 meters per second. After the third, 30 meters per second, 40 meters, you get the idea. That's what acceleration means. That rate of change of velocity, which is a vector. Take your silence as good, move on. Free fall. Free fall, you've heard of that term, I assume. We're going to define it, it is defined, as the motion under the influence of gravity only. So it's when something's falling because the earth attracts it, but we're not worried about air resistance, and we're not worried about some side wind or friction or anything, just under gravity. So if the only thing acting on something is gravity, we say it's in free fall. That's all it means. If you take this equation and rearrange it, you can say the change in velocity is equal to the acceleration times time. We just did that, if you realize it. If you're going 10 meters per second squared for acceleration, 10 meters per second squared, times 1 second later, 10 times 1 is 10. So yeah, your change in velocity was 10 meters per second. And if you're going 10 meters per second squared after 5 seconds, 10, 10, 10, 10, 10. You're now going 50 meters per second. So some of you might prefer to remember it that way. Up to you. But there's an equation to represent that relationship we just walked through. And I wrote it that way because you guys are already aware of the acceleration due to gravity. We call it G. But realize it's an acceleration, so it's a change in the rate of velocity. And its value, 9.8 meters per second squared. So that's what the Earth is making everything accelerate downward at in our wonderful reference frame here on the surface of the Earth. Yes? Okay, you're falling, you say, and at some point you're not accelerated anymore. So that means you must have decelerated. Why? What caused that? Was it gravity? No, gravity's accelerating you down, so something, see, you're a good scientist, something must have slowed you down then, correct?
Because you're not accelerating, you're decelerating?
No. If you're falling at a constant rate, a constant velocity, what's the acceleration? 0. If this is not changing, I mean, you're in mechanical equilibrium, you're constant rate, constant velocity, then that's 0, this is 0. So if you're moving steadily, there is no acceleration. Yes?
Are we assuming in free fall that it's falling in a vacuum then? Because when you reach terminal velocity, is that when the speed is pushing back?
Very good, very good. And see, we helped each other get there. Yes, terminal velocity was the term you brought up, and that's his point, that he knows that if you fall through the atmosphere, gravity's accelerating you down. Would we say that he's in free fall? In real life, no, because the air is acting on you as well, upwards, air resistance. And so you can draw a force body diagram. That's your weight. And you guys, you already know this. That's mass times your acceleration. Gravity is what's accelerating you down. And if you have air resistance up here, it's trying to accelerate you up. They're competing. And so the net force, the resultant force of these two, what's going to happen? Well, if we say up is positive, it's convention. You can define it however you want as long as you're consistent in your problem. But usually up is positive. So that means we have the force of air resistance up minus the force of weight down. If they're balanced, describe your motion. Constant speed. Notice you're still moving. Inertia. Things in motion want to stay in motion unless there's some net force acting on it. What's the net force in this case? 0. So the net force is 0, which means you have no net acceleration because these two are balancing each other. Thus, you're not changing your speed, and you're happy going along at what we call terminal velocity. That's when you're no longer going faster or slower, but falling at a constant speed until you whack the ground. At the beginning, this is larger. And so you accelerate down. But then as you slow down, these balance. If for some miraculous reason this were larger, what would happen? You'd start moving up. Do we ever see that? Do you ever see anybody falling, all of a sudden just go up again? Maybe if there's a big insurgence of wind to help, but no. But theoretically, if that were bigger, you'd accelerate up. Okay, if the acceleration due to air resistance is 4 meters per second squared. The air resistance, the acceleration due to air resistance is 4 meters per second squared. What would be your net acceleration downward? How'd you get that? That's correct. The acceleration due to gravity is 9.8 meters per second squared. That's what's trying to go down. You got 4 competing upwards. So the difference. Acceleration is a vector because it includes the vector velocity. So 9.8 meters per second squared is down. This is up. The difference. Oh, I should be good. I'll be consistent here so you can see it. I said up was positive, didn't I? Well, let's do that. That means this one's positive, correct? But that means this one is what? So my answer is negative. And that negative represents, in this case, down. See, it works out if you're consistent. The signs can tell you the direction. That makes sense? You're going to play this net game a lot, so I want to start exposing you to it. Good, good. What if you're already moving at a certain speed? I want to show you this one. This is in a footnote in your book, but I'm giving it to you because I think it'll help you. Another equation to help you. This is initial velocity. If you want to know how fast you'll be going after accelerating for a certain amount of time, especially falling, you can calculate it. Drop something from a bridge and you can figure out how fast it'll be going when it hits the bottom. You just time it. Remember I gave you the one, if you're accelerating at 10 meters per second squared, we'll approximate gravity as 10 right now. After 1 second, you're going 10. After second, you're going 20. Well, that's if you started at rest, if that was 0. What if you were already moving? I'll give you another one. So initially, you're going 15 meters per second. Let's say this was 15 meters per second. You're already falling at 15 meters per second. After 3 seconds, how fast would you be going? So you can look at it 2 ways now. There's an equation. You just plug it in and get a number. Or think of it conceptually, what that rate of change is doing. Your initial velocity is 15. Down. I'll be consistent. So, what's gravity? The acceleration due to gravity? 9.8. Down. And we're going to do that for 3 seconds. Because I don't feel like doing that. Make that 10. That makes this 30. 30 negative added to a negative 15, so negative 15 minus 10. So after 3 seconds, with an initial velocity of 15, you'll be going negative 45. Three seconds of change. If you're going to change 10 meters per second every second, 10 meters per second for 3 seconds. So I'm going to have a total change of velocity of 30 meters per second. So I'm going to be going 30 meters per second faster than I was at the beginning. Does that make sense? That's how I like to think of these. That's how I remember this formula. Well, okay, I've been using it a long time now. But initially, that's how I memorized it. Because it reminds me of that relationship of what acceleration is to velocity. Let's do enough of that. Although, yep, did that. These. This is a buggy run off of batteries. And let's just figure out what its motion is. So I'm going to be the very accurate stopwatch. And for equal time intervals, I'm going to mark its position. So we'll start here. 1001, 1002, 1003, 1004, 1005. Good enough. So we started here. After 1 second, we went that far. After the second, third second, fourth second, fifth second. Scientists observe. What do you notice? Describe its motion. Help me out. What's constant? The speed is constant. And you know that because? Describe it in physics.
There was no change in velocity or speed.
There was no change in velocity. That is correct. How do you know that? What's your clue? The distance for each equal time interval isn't changing. Correct. So you could do an instantaneous speed here, right? This distance took 1 second. Distance divided by time is speed. Tells you how fast it was going here. Do the same thing here. It's the same distance, same interval of time, so same speed. Same. So yes, the speed is not changing. Constant velocity, no acceleration. What's the net force on this car then during the trip? 0. Because it's not changing its motion. It's staying constant. What two forces are acting on this car when it's moving? Friction. Speed's a velocity. That's not a force, but I know what you mean. What's propelling it? Yeah, the battery, the engine. Sure, yeah, something's pushing it forward. That's the second one. Yeah, one's that way, one's that way. They must be balanced. The net force is 0. There's no acceleration. It's in mechanical equilibrium. There's no change in velocity. And there you go.
Well, something else that I observed
Good, yes.
is that the distance at each time interval is the same. If the velocity were to increase, they would probably, the time intervals would be further spaced out, wouldn't they?
He's wondering if we change the velocity with each time interval, how would it be different? I'm glad you asked. Let's do it. This is where I'd give you a clicker question, but I'm going to wait because until it's working. All right. This fan, you saw how it worked before. The fan blows the air that way. The air pushes on it and propels it forward. We still have friction. Let's see what happens. (1001), (1002), (1003), (1004). Good enough. Started here. After the first second, second, third, fourth. Absolutely, distance increases. Describe its motion. It's accelerating, clearly. Because in the first second it only covered this much distance. Notice, its velocity at this point, instantaneous velocity, how did it compare to the velocity of this?
Well, that was constant.
This was at a constant velocity, correct. This instantaneous velocity of this during the first second, how do you think that value compared to this guy's speed? Do you remember how far this one went the first second? To about here. So who do you think is going faster during the first second? This guy, yeah. Speed is distance divided by time. Small distance, 1 second. This one was a larger distance in the first second. So yes, during the first second, this guy was going faster. But second covered a lot more. So now his velocity is much greater than his velocity. That velocity is changing. We have acceleration. And you can see that. Each second, it covers more and more distance because it's going faster and faster. Yes? Velocity? Its velocity is increasing. Yes, what I'm going to get to next is the fact that acceleration is proportional to time. So is velocity, but they differ. Acceleration, or velocity is based on time, t, distance over time. Acceleration has that squared term, meters per second per second. So acceleration ends up being proportional to time squared. Here's another little symbol I like to use, so I might as well tell you. Little squiggly tilde represents proportional to in mathematics a lot of times, so that's what I do. And Galileo figured this out, smart guy. He did just this and noted how far it would go in equal time intervals. He'd use his pulse or music. The beat of music was more consistent. He started out with his pulse, but he realized that the pulse could change, especially, if he saw a cute lady walk into the room. But music was consistent, and the human could detect that. And what he used was gravity, because he knew gravity was consistent, a consistent force, a constant acceleration. And so he'd roll balls down the ramp, like this. Here's a heavy ball. Gives you an idea. Less heavy. And so, together, it didn't matter whether one had more mass or not. If I roll it straight, it's a little crooked. That's fairer, more fair. Okay. Darn hole on this one. This is backfiring, isn't it? enough. I think I'm proving my point well enough. You can do it straight. My point I'm trying to show is that they accelerate at the same rate, 9.8 meters per second squared, because he observed that they traveled the same distance in each succeeding second, whether it was massive or not. And this distance, he used numbers and figured out that it increases by time squared. And we'll deal with more of that next time. But any last minute questions? All right, thanks guys. Oh, sorry Brian.
So if there's no additional force, the acceleration will be the same.
If there's no additional force, the acceleration will be the same. Yes. For a given force, that yields a constant acceleration. The acceleration is not changing. The velocity would be changing, but not the acceleration.